Electricity. We see it everywhere in nature. One of the most spectacular displays of electricity is lightning, and a more subtle display is demonstrated by our nervous system in our bodies, transferring information by electricity. Electricity has been around since the beginning of time. Shocks from electric fish have been documented as early as 2150 BC. Thales of Miletus recorded observations on static electricity around 600 BC. The formal study of electricity, however, is a fairly recent pursuit for mankind, and the understanding and application of electricity has skyrocketed in a short period of time. We are still learning even today new and innovative ways to apply this mysterious phenomenon. In starting a course of study in electricity and electronics, it is sometimes difficult to know where to start. A good starting point is to take a moment to look back at the work of others, to see and appreciate how we all arrived at where we are today, and at the same time, we'll learn some useful terminology which we'll use throughout the course. Benjamin Franklin is often referred to as the father of electricity. Back in 1752, he observed electricity in clouds by flying a kite in a rainstorm, hypothesizing that lightning was electrical. A metal key around the bottom of a wet kite string jumped sparks to the back of his hand. So very little was known about electricity at the time, and certainly the potential lethal consequences of an experiment like this were not well understood. Fortunately for Franklin, he was well insulated and not in the conducting path. Others trying similar experiments were not so fortunate and suffered death by electrocution. Besides discovering that electricity existed in clouds, Franklin also observed that electricity had charge. He was the first to identify positive and negative charges. Since the time of Ben Franklin's famous kite experiment, there have been many milestones in the understanding of electricity and its behavior and effects. Much of what we take for granted today was discovered by many bright and smart scientists. Around 1780, Luigi Galvani observed the leg of a dead frog jump when a scalpel touched a nerve on the frog's leg. Galvani observed that electricity caused the frog's leg to jump, but incorrectly concluded that electricity came from the frog's leg. In 1800, Alessandro Volta had been studying the effects of how two dissimilar metals together with an electrolyte generated electricity. Because there were dissimilar metals in Galvani's experiment, one being the scalpel, and the frog's leg itself acted as the electrolyte, Volta postulated that Galvani had inadvertently generated the electricity he observed, and it did not come from the frog's leg at all. Alessandro Volta is credited with inventing the voltaic pile, which is what we commonly know today as a battery. Volta has the honor of having the unit of measurement for electrical potential, the volt, named after him. In the 1820s, André-Marie Ampère was instrumental in the study of magnetism and electromagnetics. His research was foundational in the development of motors and generators. The unit of measurement for electric current, the amp, was named after him. In 1827, German physicist George Ohm gave us the mathematical relationship between voltage, current, and resistance. The mathematical formulae are named after him as Ohm's law. The unit of measurement for electrical resistance also takes his name as the ohm. We will study these equations in detail later. The triangle with the V, I, and R are a memory aid we will use to remember the various forms of the equation relating voltage, current, and resistance. Around 1840, James Prescott Joule gave us Joule's first law, more commonly known in electronics as the power law. The power law relates power in terms of voltage and current. The unit of measure for power is the watt, which is named after the Scottish mathematician James Watt, who did extensive work on improving the steam engine. The volt, the amp, Ohm's law, and the power law are all foundational elements in the study for this course. Other notable advancements in electronics happened quickly. A selected list of achievements is as follows. Alexander Graham Bell invented the first practical telephone in 1876. Thomas Edison, one of the world's most prolific inventors, patented the phonograph in 1878. In 1880, he developed the first commercially practical electric light and also patented an electric distribution system. Heinrich Hertz in 1888 discovered radio waves. Vladimir Zworykin in 1924 developed the picture tube. Eckert Macaulay developed the first digital computer in 1946. Perhaps one of the most important developments for commercialization in electronics is the invention of the transistor. Shockley Bardeen Brattain of Bell Labs invented the transistor in 1947. Also of Bell Labs, Gerald Pearson invented the solar cell in 1954. Jack Kilby Robert Noyce of Fairchild Semiconductor invented the integrated circuit in 1958. And Ted Hoff of Intel fame invented the microprocessor in 1969. This section will look at exactly what electricity is, and then take a look at some basic electric circuits. We'll examine the difference between AC and DC electricity, and study the behavior of electricity in a circuit by exploring the properties of voltage, current, and resistance. Then we'll wrap up the theory section with Ohm's law and the power law. What is electricity? Electricity is a mysterious entity. It is sometimes difficult to describe and understand exactly what it is. To try and understand, we need to get back to basics, back to the very element of matter that makes up all things, the atom. All matter is made of atoms. This is a diagram of a lithium atom. All atoms are made up of neutrons, protons, and electrons. Neutrons have a neutral electric charge, protons have a positive electric charge, and electrons have a negative electric charge. Normally, an atom has a neutral charge. It has the same amount of electrons and protons. Electrons, however, can be easily moved from or to the electron orbitals of an atom, either by losing or gaining electrons, thereby becoming either positively or negatively charged. Electronic circuits have electrons moving through them in a multitude of ways. The study of electronics concerns itself with directing these electrons to achieve the desired effect with electronic components. The electronics designer is the coach, the components are the playing field, and the electrons are the players. A definition of electricity states, electricity, a form of energy resulting from the existence of charged particles, such as electrons, either statically as an accumulation of charge or dynamically as a current. The definition further refers to two types of electricity, the first being static or static electricity, and the second dynamic or an electric current. Static electricity is exactly that. It is an electric charge that is not moving. A great example of this is rubbing a balloon on a sweater or your hair and sticking it to a wall. The charges sit on the surfaces of the object, yet don't move. An imbalance of electric charge causes the surfaces to attract or repel. Like charges repel, and opposite charges attract. Let's take a look. Here we see a wool sweater, a balloon, and a wall. We see the charges on each object by the red positive charges and the blue negative charges. To begin with, none of the objects have an imbalance of charge. All the surfaces have an equal amount of negative and positive charges. As we move the balloon on the sweater, we can rub off some of the electrons onto the balloons and have a net positive charge on the sweater and a net negative charge on the balloon. We can now see that the sweater and the balloon are oppositely charged, so they attract. As we move the balloon towards the wall, we see something interesting happening. The negative charge on the balloon repels the negative charges away from the location of the balloon. So where the balloon and the wall meet, we have a localized opposite charge, negative on the balloon and positive on the wall, which is why we can stick the balloon to the wall. Opposites attract. Electric current is what happens when electrons flow through a conductor, such as copper wire. Electrons move from atom to atom, resulting in an electric current. We can see this here in a very simple circuit of a flashlight, consisting of a battery, a filament light bulb, some wire, and a switch. The animation gives a visualization of electron flow or current flow through an electric circuit. Any electric circuit, by definition, is any arrangement of electrical components connected so that there is some form of current flow. Typically, there is a current or voltage source and a number of components connected with wire or circuit traces or other conductive means. Circuits can range from very simple, like a flashlight, to very complex, like a computer. No matter how complex a circuit is, it can be broken down into a number of simpler circuits. All circuits can be analyzed as series or parallel circuits, or a combination of both. A basic series circuit consists of a source of electrical energy, like a battery or a solar cell, a load which does the work of the circuit, like a light bulb or a motor, some components and other devices, and of course some conductors to connect everything together. For a series circuit, everything is connected in series. In a series circuit, all the current flows through every device. A break anywhere in the circuit interrupts the flow of current. The circuit to the right is a series circuit. It consists of a battery as the voltage source, two light bulbs as the load, and a switch together with the connecting wires. All the current flows through each and every piece of the circuit. We see that if we open the switch, breaking the circuit, the current flow stops. Closing the switch, completing the circuit, current flow resumes. In parallel circuits, there are multiple paths for current to flow. Multiple components are connected in a ladder fashion. Current can flow through components without first having to flow through another component. Here we have a parallel circuit with multiple light bulbs. Breaking any of the rungs of the ladder doesn't affect the other rungs. To disable the entire circuit, we must first break the circuit at the power source. Completing the circuit at the source resumes current flow to the entire circuit. Many circuits are a combination of parallel and series circuits. Complex circuits have many paths for the current to follow. In this example, we see the current flows through a complex circuit. The animation gives you an idea of the different current through the different circuit elements. Many circuits are very complex. Analyzing them mathematically is complicated and beyond the scope of this course. However, a large multitude of circuits are of simple complexity. Analysis reduces to identifying the series and parallel sections and combining the analysis on each section. Can you spot the series sections and the parallel sections in this circuit? We need to understand that all circuits, no matter how simple or complex, are made up of a combination of series and parallel circuits. Knowing this will help us design our circuits with confidence and skill, ensuring that they reliably do what was intended. All the circuits we have looked at so far are DC circuits. DC stands for direct current. It means that the current is flowing in one direction only. DC current is generated by DC sources, such as batteries or solar cells. The battery in your car or flashlight generates DC current. If current flows in two directions, alternating, we call it AC current, which is short for alternating current. Alternating current is generated by generators or inverters. Normally, our house current is of the AC variety. It alternates 60 or 50 cycles per second, depending where in the world we live. Here we have two identical circuits of the flashlight. Identical, except that the left circuit is powered by a DC battery, and the right circuit is powered by an AC source. We can see in the DC circuit current moving only in one direction. In the AC circuit, we see the current moving back and forth. In the DC circuit, from the voltage graph, we see that voltage is constant over time. In the AC circuit, we see that the voltage alternates in the form of a sine wave. This is characteristic of currents produced by generators in a power plant. In this course, we'll be dealing primarily with DC circuits, although we will take a look at some special cases of some special AC circuits. To get a feel for the properties of electricity and its behavior in a circuit, we need to understand in a general sense what the quantities of current, voltage, resistance, and power represent. We can use a water analogy, comparing electron flow through a conductor to water flow through a pipe to help us understand these properties. Current. Electrical current is the flow of electrons through a conductor, just like water flow through a pipe is. We can have small and large currents depending on how much water flows through the pipe in a given time. Electrical current would be the amount of electrons flowing through a conductor in a given amount of time. Electrical current is measured in amperes, or amps for short. Voltage. Voltage is often referred to as the potential of an electric current. Using the water analogy, it is analogous to the pressure of the water in the pipe. The higher the voltage, the higher the pressure is. Pressure in a pipe depends on the source driving the flow, such as a pump. The same is true for pressure or potential in an electric circuit. The higher the voltage source, the greater the pressure or potential. Electrical potential is measured in volts. Resistance. Resistance is quite simply that, resistance to current flow. All materials resist the flow of electrical current to varying degrees depending on their properties. In the water analogy, this equates to restrictions in water flow in a pipe due to bends, fittings, valves, pipe friction, etc. Electrical resistance is measured in ohms. Power. Power is the amount of work being done in a circuit. It is the product of current and voltage. We have to think of work as a result of what is done and the energy consumed to produce that work. In the water analogy, we can think of how the flow and pressure act to turn a water turbine, for instance. In an electric circuit, this would equate to how the current and voltage work to drive an electric motor or a light bulb, for instance. Electrical power is measured in watts. Here we see our electrical circuit alongside our water analogy. The electrical circuit has a voltage source, some conductors, and a device for work, that is the light bulb. We can see the current flow represented by the electrons flowing through the conductors. In the water analogy, the power source is represented by the pump, the conductors by the pipes and tanks, and the object of work, the turbine. As we increase the voltage or pressure, we see that the current flow increases and also more work is done. That is, the bulb burns brighter. On the water analogy side, we see that the height of the water in the tank increases, representing the increase in pressure. The water flow increases in current, and the turbine spins faster, showing that more work is done. This simple water analogy gives a tangible illustration of how the electrical properties of current, voltage, resistance, and power relate to one another. Now that we know what current, voltage, and resistance are, we're ready to look at some math. Ohm's law is a simple equation that relates current, voltage, and resistance in terms of one another. The triangle with the V over the I and R is a memory aid to remember the different versions of the equations for Ohm's law. V represents voltage, which is sometimes designated with an E rather than a V. I is for current, and Rs for ohms. The units for voltage, current, and resistance are volts, amps, and ohms. We can use Ohm's law to solve for one in terms of any of the others. So knowing any two of the three components, we can solve for the other. Current is the voltage divided by the resistance. I equals V over R. Voltage is the current times the resistance. V equals I times R. And resistance is voltage divided by the current. R equals V over I. Here we have a visual demonstration of Ohm's law. We can see the effects in the circuit by varying voltage and resistance with the sliders. Increasing voltage results in the current in the circuit increasing. Increasing resistance causes the current in the circuit to decrease. Decreasing voltage results in current decreasing. And decreasing resistance causes the current to increase. The mathematical relationship between power, current, and voltage is known as the power law. Power equals current times voltage, or P equals I times V. The unit of measure for power is the watt. This is an extremely useful equation, so remember it. We will use it a lot. Combining Ohm's law with the power law allows us to solve for power in terms of current and resistance. Here we see a chart showing all the possible equations relating current, voltage, resistance, and power. In the upper right quadrant, we see the equations for voltage in terms of current, resistance, and power. In the lower right quadrant, we see resistance defined in terms of current, voltage, and power. In the upper left quadrant, we see current defined in terms of voltage, resistance, and power. And finally, in the lower left quadrant, we see power defined in terms of current, voltage, and resistance. Keep this chart close by. It is a handy tool as we design our circuits. So this brings us to the end of our theory section. By now we should have a good understanding of what electricity actually is and the difference between static electricity and electric current. We should be able to identify different types of electric circuits: series and parallel, simple and complex. We should also understand the differences between alternating and direct current and their sources. Through the water analogy, we should have a quantitative view of voltage, current, and resistance. The foundational equations of Ohm's law and the power law should now be a part of our knowledge base. These basic foundations have equipped us well as we now move to more practical applications in circuits.